Welcome to Google DeepMind, the podcast. I'm Professor Hannah Fry. Right, agents. They are here, or almost here, and they are probably all anyone is going to be talking about in 2025. But they are definitely not new. My guest on today's episode is someone who last came on the podcast in 2019 to talk to me about the multi-agent system he was working on. It could beat the professional StarCraft players at their own game and eventually went on to achieve Grandmaster status. But how have agents evolved since then? What can they do now? How have the advances in language models and multimodal AI changed things? And how do you possibly go about building something that can make autonomous decisions on behalf of its user? Now, I should tell you, if you want a primer on agents, you can watch our episode with Frederick Best that we recorded over the summer. But for now, Oriol Vinyals is Vice President of Drastic Research and Co-Tech Lead of Gemini. And it's fair to say we've got quite a lot to catch up on. Oriol, welcome back to the podcast.
Hi, thank you for having me.
What is Drastic Research?
Well, I keep telling my team they have to think drastic, meaning don't just do the incremental stuff that everyone is thinking about. Try to drastically think what will happen in a few years' time and then try to backport those ideas and then execute today with that mindset in mind. So that's what drastic means. But yeah, it's a word that I use a lot.
I think when I last got to see you, you had been working on an agent that could use a keyboard and a mouse to do things like draw pictures in Paint or play StarCraft. And, things have moved on quite a bit since then.
So those agents, at the time, you took sort of a very generic set of principles, very simple principles in the field of machine learning. And you would basically specialize a model on one task. And what we were doing at the time is have a curriculum of tasks that were more and more and more difficult, right? So when we last spoke, for instance, in video games, we were looking at StarCraft, which is one of the most complex modern strategy games out there. And of course, DeepMind is notorious for having started the trend with Atari, which is a fairly simple game of, left, right, hit the paddle and hit the ball and, off you go. So that sort of is what the algorithms themselves, we try to push for them to be very general so we can keep climbing this ladder of difficulty, curriculum of games, and doing more and more complex things. And right now, what has happened is even the models we train are broadly applicable to many more things than the models we developed back then were, right? So think about the process of creating this digital brain hasn't changed that much, but what that brain was able to do was reasonably narrow, although very complex, like playing StarCraft or playing Go. Right now, these models can do quite a lot more broad applications and, of course, talking to us, chatbots, et cetera, et cetera.
So back then, like reinforcement learning was your main kind of lever, I guess. How different are things now?
Yeah, so algorithmically, actually, the process of, AlphaGo and actually AlphaStar, those two had the same set of sequence of algorithms applied to creating this digital brain. And it's not actually that different from how current large language models or multimodal models are created today. There's two basic steps that have been pretty constant throughout many years in many of the projects that we've worked on, which we can call the first one pre-training or imitation learning. That is, you start with random weights, you have an algorithm that will try to imitate lots of data that humans have created to either play a game or, in this case, all of the internet, all of the knowledge available to us. And in that first stage, you just adapt the weights to try to imitate that data as well as possible.
And these weights are essentially inside each of the neurons is like a series of numbers that kind of describes how it's connected to everything else.
Yeah, so these are basically, there are units of computations that are neurons, and the connections between neurons are what actually you have as weights. So you can imagine that there's a neuron, there's a few neurons connected to it, and you're basically adding all the activations from the incoming neurons there multiplied by the weights, and those weights are the only things that move. and the inputs excite the neurons. It's pretty much how, a brain works with some, freedom of, creativity.
Okay, if we were to do an analogy, it's almost like you've got the neurons and you're like, water is flowing through it and the weight is like the width of the pipes between the neurons.
Yeah, that's right. And then you can imagine having millions of neurons and billions or even trillions of pipes. And that is what we spend most compute actually training these models, especially language models, is in this pre-training or imitating all the data that we have available to us.
Okay, so you've now got this gigantic network with loads of pipes going between all the neurons. And that's your imitation phase. Done. Next bit, if you were doing, say, AlphaGo or AlphaZero, you would then get it to play itself.
Yeah, so this model now is reasonably good at playing moves that look human-like. So that means, of course, it's the sentences are very plausible sentences in English, or if it was playing a game, it would sort of click things reasonably to move, pieces on the board and whatnot. But what this model hasn't done is learn that these actions yield reward, right? That's the bit of reinforcement learning or post-training, which is the second phase of training. So you can write a poem by just how does a poem on the internet look like on average? But then the question is, well, I want only the good poems, right? So how can I further adjust these pipes based on sort of a signal that now having written now a whole poem would give a score of 0 or 1, let's say, right? And if it's a mediocre poem, you get a 0. If it's a good poem, you get a 1. Again, for a game analogy, which is what we've used reinforcement learning traditionally, if you win at the game, you get a 1. If you lose, you get a 0. And then you further adjust the weights. But now, instead of imitating humans, you're just saying, forget, I want to go beyond what humans could do and try to really get all my poems to be the perfect poem, right? Or all my chess games to be the perfect game. And in language models, this second phase, which is reinforcement learning, post-training, tends to be fairly short-lived because we do not have access to super clean reward as, you've won the game or you've lost the game when you do self-play in traditional board games, for example.
So once that's done, right, then that's all the stuff that goes on behind the scenes. And then you're like, whoosh, hold it right there.
Yeah.
Stay exactly where you are, everybody. We're going to take just basically a snapshot of this entire network. And that is what you actually get to access as a user.
Yeah, so now this amazing process finished. These weights are super precious, right? So this configuration you found, you've really spent months to finesse it, to tweak everything. And now you sort of will never move it anymore, right? So training is over. You're not changing the configuration anymore. You might want to make it super efficient, right? So say like you find that, oh, look, this neuron is not that useful. It's not used for anything. You remove it so everything becomes faster and cheaper to run it at scale. And then as a user, you just get the same weights. Everyone gets the same weights we've trained. That's what we call Gemini 1.5 flash. That just means a set of weights that are frozen, will not change, will not further train or anything. So those two steps actually pretty much are identical from AlphaGo to AlphaStar to current large language models. And of course, there's details that matter, and the field has evolved certainly, but the principle is pretty much unchanged, actually.
Because under the hood, as it were, there are differences between, I don't know, I'm thinking like DQN here, which was the Atari example, or the types of algorithms that are used in AlphaGo, or then again in the large language models. Like the architecture is different, right?
Yeah, so there's a few components that go into then what the digital brain is. One is the architecture, right? So there are these neural networks. Now we have the transformers, which we certainly didn't have back in the DQN days. So there's always some sort of breakthroughs in architectures that are better at learning from the data. But then from transformers to today, it's almost all about little tweaks. I mean, even if you look at AlphaFold, which also is fueled by a transformer, what that teams do for years sometimes is just to find little tweaks on, hey, let's remove this set of neurons, let's add another layer, let's make this a bit wider. So the brain shape changes a little bit, and that makes it or breaks it sometimes in terms of the performance achieved.
So if these are all the things that have been achieved so far, I mean, the goal, as I understand it, is to create more agentic behavior, to kind of get these things to make autonomous decisions. How did these help to achieve that end?
Yeah, so let's zoom in a little bit on the current trend. We call it large language models, but they're multimodal. I think we had an episode earlier covering heavily the multimodality aspect, how good it is to be able to add an image, then ask something, a follow-up question, and so on. So this core, we will still improve it, right? These set of weights that do these amazing sort of inferences about the input, right? What's this image about? What's the user asking? Can I write a better poem? Can I just make it longer? Whatever, like all these interactions we have all like kind of get to play with these days. But this is just a component, and we can think, hey, this is now our CPU, and we can add more to it, around it. What if the model could go off and do research for you? Could, for example, right? One example, we were already thinking about that back in the day. I could ask a model, a language model or visual language model, to learn to play the game of StarCraft. That's a very different approach to say, create one agent that does play the game. In this other example, right, it could go online, watch videos about the game. It could, of course, download the game to start interacting with it, to learn, oh, yeah, like I know how to, I get it. Do research online, go to forums, read the forums, go play and figure out that it's weak at this thing and improve and so on. And after literally, it could be weeks, it sends you an email that says, I now know how to play the game, let's play, right? That's not a reality that's that far away, but these models all of a sudden actually do something, take some actions, and learn anything new that is available to them. And that's pretty powerful to think about. It's what pushes the generality the most, and that's what makes kind of the AGI, as many people call it, feel closer.
So if I understand it correctly, then it's almost like the stuff that we have at the moment, the large language models, the multimodal models, whatever you want to call them, that's like kind of the central core. But the next step is that you build stuff on top of that central core that it can go off and take off the stabilizers and kind of go off and do its own thing.
Yeah, exactly. If it has access to all the knowledge and it can sort of use its time to do some proper research, write hypotheses, write some code and so on, and take its time to really answer very, very, very complex questions, then the possibilities now have broadened quite drastically. Although, of course, we're not going to need that for everything. If we ask a question like, hey, what I like rice, what should I prepare tonight? Probably no need to do a very deep dive into thinking or just going off for 3 weeks. Then you'll probably not be very happy about the waiting time, right? But I think that's kind of to push the frontier. You're giving a digital body to the computer, so it can not only just think and give an instruction or a word output, but it can also go off and do things online or on documents that you might upload or whatever, and ask very, very complex questions and personalize to you, et cetera, et cetera.
I like that idea, this central core, and then you're giving it a digital body. You've got the electric brain, and now you're giving it a digital body. It's kind of
exactly.
Nice. Okay, so in terms of the electric brain then, in terms of this core, this processor, let me just ask you a bit about that. I guess we should be thinking about Gemini here, right? Which is essentially what we're talking about, the multimodal model that you guys have. I know that one of the big ideas for large models was just to scale it up, right? To get them bigger and bigger and bigger and bigger and bigger. Do you think that the results that we've seen from scaling have sort of plateaued by now?
Yeah, it's a very important question, right? We have studied how, as you make the models larger, that is, how many neurons literal these models have, how do they become better at certain, tasks that we have clear metrics from the whole machine learning community. For example, one that is very simple to understand is machine translation, right? So how good the models are at translating between two languages. As you scale, as you go from millions to billions to potentially trillions of neurons, you can see the performance keep improving. Now, even when you do those studies, one trick is that it looks linear, but you have to plot logarithmic axes, right? What that means in lay terms is that, let's say from the last 3 years, we had some improvement. You shouldn't expect the same improvement in the next 3 years. It's actually exponentially hard to get there, right? So that means the compute investment, which of course also advances at a super linear rate, but perhaps not as good as this sort of trend suggests, you would just see some diminishing returns because simply scaling the x-axis, right, the number of parameters, you need to go 10x to see the same improvement. And that just creates some pressure to, hey, maybe we can't scale as much and we need to think about other ways to scale to make the models better.
The example I give to my students is like, if you've got a room that's really messy, the first 10 minutes that you spend tidying is going to make a massive difference. You pick up all the dirty plates, put away all the dirty washing, fine. But once you're like 7 hours in, that 10 minutes, extra 10 minutes, it's not going to make any difference at all. And that's essentially where we are, right?
Yeah, that's exactly a very good analogy. And in fact, that analogy can even apply to then the performance of the models. Even if you have extremely good performance, if you want these models to be 100% factual, right? They will never make something up. We know that if you probe them, you can make them say some things that are not real. Even that last mile also is super hard, which creates some interesting challenges to deploy then at scale.
So, okay, I hear what you're saying about how there's diminishing returns in all of this, right? But in terms of how you make these things better, how you make these models better, is it just data, computational power, and size? Are those the only things, the levers that you have to pull?
Yeah, so certainly if you froze the architecture, let's say for the next year, no innovation, we just scale because there's better hardware coming up.
Just make it bigger, yeah.
Make it bigger. That certainly would have a trend that would look okay. But what's happened, and certainly in Gemini, we have other innovations, like other, tricks, techniques, details about how to order the data that you present the model with, to the details of the architecture, to how to run the training process, how long to run it for, what kind of data do we actually present the model, how do we filter, do we present more data that's high quality, less data that's low quality, all sorts of different, what we call hyperparameters. And of course, other algorithmic advances. We also investigate fairly carefully because the process of training a model is expensive. So we need to be extremely careful with piling up innovation so that eventually when we are ready, we have enough innovation and also probably we'll have a better scale to run for the next iteration of models. We run it and then we get algorithmic, not only breakthroughs through data and compute.
I guess the other thing about this scaling stuff is that there's no limit really to the number of nodes that you can put in. Maybe there's sort of no limit in theory to the computational power that you put in, but there is a limit to the data that you can put in, right? There's a limit to the number of human words that are out there.
Good point. So I think, there is a limit on the nodes because how you scale these models is, they don't fit on one single chip, hardware chip. So now you have a mesh of chips, they're communicating, there's certain limits like speed of light, et cetera, et cetera. So there starts to be a time where the efficiency of training such a big model also just not worth it, even from a utilization of the hardware at your disposal. But very good point, right? The other bit that is critical on this pre-training, imitate all the data is that we do not have what we call infinite data regime. There's finite data. And so as soon as the models need to, you can think, let's train on all the data. If you want to train
everything humans have ever read,
everything, like all of the internet. So we're just starting to think, okay, we're running out of data. There are techniques like synthetic data. Can we write or rewrite existing data in many different ways? Languages would be obvious ways to think, hey, you could write the internet. It's mostly in English. 60%, I don't know what's the exact percentage, but there are ways to rewrite the same knowledge in different ways. We're exploring those. That's kind of a research area that many people are starting to invest because if you run out of data, the scaling laws punish you even more.
So for example, then you could get Gemini to write its own version of the internet and then use that to train a new version of Gemini.
Yes.
Is there a danger, though, that if you start feeding in the output of the same model, that you can end up creating these little, unhelpful feedback loops?
They certainly can, do some interesting experiments to test ideas like this one you just mentioned. And indeed, that is not, on the surface, not a good idea. Like the model suffers if you just ask it to recreate all of the internet. And indeed, a priori, from a information content point of view, look, this data set has the information that it has. How could you create new information, right? I don't know. These ideas might help a little bit because there's machine learning deficiencies that we're not at that fundamental ability to extract all the information truly from the internet. I mean, we have good algorithms, but they're not perfect. So we'll see. Yeah.
I mean, I guess I just want to think about that a little bit more because it's a really interesting idea. Because, of course, naively, if you did it without thinking, then it's like the new version would be sort of have the biases in it, and then the new version on top of that would be more biased, and you'd end up sort of spiraling away from the original human one. But then what you're saying is as though in the original human internet is sort of embedded these conceptual connections. And if you can extract those, I'm sort of thinking almost like E equals MC squared, right? If you can sort of find the E equals MC squared for human concepts and then just generate new data using that alone, then that seems more realistic.
Yeah, exactly, right. And I think that's where you start hitting, are these language models just repeating what's online and not being able to create anything new? Or are they learning a world model truly that you can then, from the principles it extracts, possibly generalize beyond what the data has? And under the more optimistic version, which I tend to believe more, we can push the limits of data a little bit more than the current limits that we have. That being said, there are some data sources that we haven't quite seen a breakthrough, like video data. There's a lot of it. And we haven't quite seen a moment of take all the video data where you probably can derive a lot of knowledge, a lot of laws of physics, a lot of how the world works, even if there are no words associated with the videos necessarily, and extract that knowledge. Even that, I don't think we tapped into that source.
And it doesn't work that way?
Right?
Or you don't know?
Yeah, it feels like it should. Even how we learn, we learn, there's some language learning in the early days, but we learn by also observing 3 dimensions and so on and so forth, right? So there probably is more knowledge that we haven't extracted. What obviously we've gotten pretty well at, and you can see by testing the models, is connecting the concepts present in the video and then you can do amazing things like, hey, take this full-hour video and just extract me 3 interesting moments, right? But the model itself, has it actually used that information directly? Probably not.
Oh, I like this so much. We were talking to Jeff about with multimodal models, if you get these models to just watch all of the videos that have ever been created, can it quite literally extract what gravity means as the concept? So, but what you're describing here, if I understand it, is that at the moment, it can tell you what's in the video that it's seen, but it can't then say, and, E equals MC squared. Or if you showed it pictures of the night sky, it wouldn't suddenly be able to predict the planetary motion in the same way that human astronomers did.
Yeah, exactly. The shortcut we're taking here is that the data we train, when we train on images and or videos, we almost always have a text representation associated with that modality, right? So it could be a caption explaining what this image has or this video has and so on and so forth. And that makes, of course, then it's incredible, right? You can put a picture of a homework and with a little drawing, conceptual, and it will connect and do quite a lot of good logic just based on that. But what I'm saying here is, could I just take videos, no language, and then train a model to then understand what's happening, maybe even in a way derive a language, maybe it's obviously not going to be our language, and extract those concepts? And that has not happened. And it probably will.
Just going back to what you said at the beginning about there's 2 phases to basically all the models that DeepMind have built.
Yeah.
The imitation phase, which is what we've been talking about right here, but then the reinforcement learning phase on top. And I know that AlphaGo and AlphaZero and many more got better by playing themselves. Does that apply here as well?
Yeah, that's one of the main open challenges, like scaling not only pre-training, but post-training or reinforcement learning, right? So the beauty about reinforcement learning in games is that there is a set of rules that are coded, and if you've won, you know you've won. There is kind of a program that if you play chess and you've won, it will check everything. Okay, that's a checkmate. Yeah. Congratulations, you've won the game.
A clear metric of success.
Clear metric. Now in language, much trickier, right? Like, is this a better poem than this? I mean, good luck discussing this even amongst us, right? So it's the generality again makes computing exactness very hard, right? Is this a better summary of the movie? Is this the most interesting bit of this video? It's very hard to quantify, but we can try, and we do try. You train a model, and based on some human preferences, roughly you just say, okay, try to now generalize. So I ask a model to criticize its own output. It's not going to do that bad. It's going to be good maybe, 80% of the time, which is not terrible. It can give you some signal. But at the point you start saying, well, now you climb this metric. You have this imperfect way to assess performance, but we're going to start training against this reward that is not perfect. What the model is going to do is exploit the weaknesses of the reward, right? Maybe using the chess example. Imagine that I had a bag, and if a pawn is in a certain position, you always win. And it's a position that no one would play ever. So maybe no one knows this exists. But now you ask an algorithm to please explore everything and try to discover how to win at this game. All of a sudden, you're going to find, if I move the first pawn just to this position, no one plays this opening, you've won the game. Certainly, you have the algorithm has nailed the game, and then a researcher goes and sees how you play chess, and it's just terrible.
Naughty AI, right? Basically, that's what we're talking about.
So that's the challenge, right? Basically, you're finding exploits rather than really learning what a good poem means truthfully, right?
Can you not just add in another player, right? So add in another model, which is like the kind of ultimate arbiter.
I mean, good suggestion, but then the problem is, how do you train that model, right? Like, we have only a finite notion of what's a good poem by some experts that we might ask, hey, compare these two poems and so on. So there's just a limited amount of data we have to train these arbiters. So the ground truth might be to ask someone that is the expert, of course, and if we could, we would, but that's not scalable, right? Then imagine how slow it would be to say, okay, like I have a parameter update that in 3 seconds I found. Now, please review these 10,000 things by an expert, because that's the source of truth, right? So, and we don't have enough data to train a good enough reward model. So again, there's some ideas, but intuitively, you clearly understand, but the problem is we don't have access to the ground truth.
I mean, that's it. It's like you're feeling around in the dark with oven gloves on. Right?
Yeah.
It's like, you're not even completely sure that there are solid objects to grab onto. Okay, so if that's the core then, right? That's the electronic brain. And now we're building the digital body. So what kind of capabilities do you want that digital body to have? Like reasoning, for example, because there's been quite a lot of work on that too, hasn't there?
Yeah, so you start thinking, well, what are the main sort of surfaces that we would be able to give these models limited access to, so they can see beyond what's in their weights, which are frozen, to be able to gather knowledge or do maybe something a bit more complex than just predicting the next word from just what they have in context plus what they have in their weights. And so, obvious things that come to mind is giving them access to a search engine. That's what we do very well at Google. Another one is to give them the ability to run the code they write, right? And then, of course, maybe even more broadly, that could be more general, is giving them the ability to maybe interact with a browser that has access to the internet, right? With all of these, you always have to be careful to sandbox. That just means protect these environments so that the models, even if they're not that advanced, wouldn't do something that is unintended, right? So there's the whole like safety aspect of this, that as you move beyond the model, it starts to be quite interesting. But if we just in kind of dream what would be possible, right? By having these tools available to the models, all of a sudden, they can start doing much more advanced things beyond what was the training corpus that we used at the time, right? They can rely on the latest news to explain us or to summarize what was the main thing yesterday that happened. All these kind of things, you need to give them these tools.
Okay, so how does reasoning fit into all of this then?
Yeah, reasoning is interesting, right? So what I described could be summarized as, hey, I want to know what happened yesterday. Then I could just say, look, maybe personalize it a little bit, right? So I could describe in words, I could say, hey, model, I'm Oriol, I'm interested in this and that. My political views are this or that. Give me like a positive take on the news yesterday, right? And the model would probably search, right? Retrieve all the news, and then given what I ask it to do, just do it in a way that I like and I find it enjoyable. Maybe if I don't like it, I can even go and then say, I didn't like this, or this is not a good joke, and then we could iterate a little bit in a conversation. Now, reasoning is a bit of a different axis of scaling, right? And so you could imagine the model deciding what kind of intermediate steps to do to give me a better answer, right? So imagine there's like 100 news outlets that Google search retrieves. Maybe the model decides, hey, I'm just not going to read this and just try to summarize it all at once. I'm going to summarize each of the 100 articles first, right? So that means the model decided, I'm going to write a summary for each of the 100 pages. I'm going to write it not to the user, to myself. And then now it has 100 summaries. And maybe the next step it decides to do is, I'm going to group these by topics. Then it decides one of the articles looks suspicious. So maybe it goes online and checks if in any forums someone discusses like, oh, this might be like sort of not truthful because of the author and so on and so forth. So it can do a lot of steps to do research. And, it could do this for quite a while. And only when the model says, well, I think now I have a much better quality answer, then it will give you the few word summary. But now it had all this time to do much more processing on the information that was available to it. And that inference time compute, we hope that the more time we give to the model, the better it's going to summarize the news, the better it's going to write a poem, the better it's going to, of course, do math. But that's certainly another axis of scaling, which we're starting to quite unlock. We hope to unlock. And again, we'll break a bit of the scaling laws and the limits that we see in pre-training, pure pre-training.
Does this also include planning? Like, could it look at your calendar, work out when your payday was, maybe know that the January sales are coming up soon, and tell you to postpone booking your holiday for a few days?
I mean, that can get very complex. But of course, when you factor in things like personalization and like when to do things because of all the other things that are ongoing, right? You have more sources of information. You need to collect them and then give the best answer. And it stops being what color is the sky, which is not that simple to answer. I was thinking about that example. I mean, we had a very early paper where we have that example as, something that language models can do amazing, right? You don't program them to answer, but they answer. But then actually, even the answer is quite nuanced if you start thinking, planets and what time of the day, I mean, is it cloudy or not, right? So the thinking and the planning, it can definitely be, that's something that these models can do.
I'm reminded I had a conversation with Demis probably back in 2019, and he was talking about the Kahneman-Tversky ideas of how the human brain has almost two systems of thinking, the sort of quick, instinctive, intuition-based, and then the much slower, calculated, sort of the way that you do maths and chess. Yeah. And Demis was saying that kind of that second one has been traditionally easier for us to do with computers, but that now we're seeing the much quicker, instinctive stuff. But I mean, you're sort of talking about putting the two together, right?
Yeah, right. I mean, probably what Demis was talking about is systems too, which is indeed one that you reflect a bit more. And in games, it's very clear, right? You just could say, oh, this move feels right. You just move. But if you think and ponder, you might get to a better move. The challenge is that now, because we are in such general direction, right? These models can do anything. I mean, anything, literally. You just do whatever you want. I mean, upload an image, talk about the news. So what it means to have this deeper thinking is so domain specific that how are you going to do that? And I mean, there's a few answers, but the one I like is like, well, these models are very general. To add the ability to think on top of a very general set of capabilities, you probably need a general way to think. And so you use the model itself to generate how it should think about anything. And the model will come up with, oh, like I'm going to summarize each article. I'm going to do this and that and that. And it is not us programming it. That's a very deep insight. Now, is it the only way to do it? And is it the best way to do it? Early days, 5 years, we'll see.
Exactly. I'll talk to you in 2029. Yeah. Okay, I'm thinking now, though, also about lots of the things that felt very important back 5 years ago. And a lot of it was about inspiration from neuroscience. So I suppose in a way, here you're talking about planning and reasoning, but memory was the other really big one. And has that kind of come through? People talk about long context and short context a lot. I suppose that sort of is working memory in a way, isn't it?
Yeah, I mean, there's techniques that are out there that you can apply to a language model. There are, at the very least, 3, and they're reasonably simple to explain, right? The first way in which we have a system that memorizes all of the internet is by literally doing the pre-training step, right? That's literally a memorization step in a particular format, which is we have these weights, they're random, and then we assemble them in these amazing architectures. Now, the second level is maybe I explained a little bit how you would give the tool of a search engine such as Google to the model. That you could claim is a sort of what neuroscientists would call episodic memory, which, as a human, maybe it's like, we have these memories from a long time ago. They're not very precise, so they tend to be a bit more fuzzy, right? Like if I have to think, oh, what was my first day at Google? I remember bits and pieces, or being in a room, or someone I met, or whatnot.
The gist.
The gist, right? Now, interestingly, these models maybe don't have that limitation, right? You can literally get an article written many years ago online, and it's going to have all the images, everything will be perfect, reconstructed perfectly. So that second mode, called episodic memory, clearly we're seeing that when you integrate especially powerful search engines into our models. And then the third one is what you could call working memory, right? Which actually the whole of thinking that I describe is one of, right? Like if we take every news article, but then we want to create summaries, find how they relate to each other, criticize some of them, this starts to combine working memory, meaning I'm going to have a scratch pad of the summaries, the issues that I think I'm finding. And that, when we call short or long context, generally we mean this last bit, like the working memory, whether you have 1,000 tokens, which means I couldn't possibly do much, right? I can retrieve articles, it's already over 1,000 words, not much I can do to summarize them. Or it can be massive, in which case you have many more possibilities to do reasoning on top of that, and so on and so forth. And so one of the breakthroughs of the year, actually, we're still in 2024. It was just to enable millions of tokens in context, which enables many things. You can retrieve something from the past, but then bring it forward and then do a very detailed analysis. That's a bit of the examples of, we have a movie, we can upload like a movie or like some very long video and start doing summarization. The fact we kind of upload it is more episodic memory, but then now we have it in memory. It all fits in memory. We can do quite a lot of associations within each frame, each object in the movie, and so on and so forth.
Is a longer context window better always? I mean, because I'm just thinking about, I don't know how much you guys are still using neuroscience as an inspiration for what you're doing, but I mean, the human memory, like there's a limit to the working memory, right? Like there's certainly sometimes when you're like, my brain is full and I'm done.
Yeah. Sometimes brain is an inspiration, but computers certainly have advantages we should build on its strengths, right? So perhaps the fact that they can have literally in memory, like, every like Wikipedia article, whatever it is, we can't. But if the model can, well, there you go. You have new capabilities. But also, it might be too confusing to have too much information, even for these neural networks. So it might be a good idea to compress. So that's where you probably want to push for getting some inspiration for how we might do what we do, which is quite amazing, right, in terms of memory retrieval and so on.
Yeah. This is why you're leading up drastic research.
Yeah,
right.
that's, I mean, what we want to do with the models should be definitely inspiring and forward-looking. And then what are the main limits of the technology? And then try to, of course, place the bets and inspire the teams to finding solutions around the critical components.
But some of the bets that you've already made have come off. I mean, I know there's been a big announcement of, a dizzying number of new features that have just come out. Can we talk through some of them? But then maybe also talk to me about the different skills that we've already spoken about and how they appear in each of these.
Yeah. So we have quite a few sort of systems around our best Gemini models. So one of the things that we've done is update to 2.0. We're seeing a generational leap. Even if you say, look, let's not scale anymore, can we get better quality? So we've done it sort of again. These models are faster, they're cheaper, and they're actually better.
Basically, Gemini's got better.
Yeah, Gemini's got better, but not only because we scaled. I guess that's
sure.
That's kind of one of the main messages.
Tell me more about the agentic capabilities that you've brought to Gemini.
Yeah, so we're releasing a companion in Chrome where you can just type to do a task that maybe, some of these tasks are tricky because I partly enjoy them, but also partly don't like them. So I'm thinking now very clearly about trips, okay? So you travel and you look for hotels or flights or whatnot, and a lot of it feels like, I wish, this could be automated, but at the same time, I wouldn't just want to not be part of this journey, right? So I guess the kind of thing we're releasing is something that hopefully will automate parts of the more trivial steps or repeated or things that need automation because I can't be bothered to click everything, right? So we're adding sort of an agent that you can ask it to do something for you, and then it's gonna, again, through thinking and through acting on like kind of the basic clicking on links and so on, try to solve the task for you, right? And that's quite an exciting both research challenge, opportunity, because it's very general environment for a very general agent and model ultimately. And some examples that we had, again, in the early prototypes is, we can ask to play a game, which of course goes back to the roots of DeepMind on the browser. And it kind of did okay, right? It finds a website, it starts playing the game. It's kind of a cool connection to the more general you are, then the more you can treat environments where you had specialization in the past as now, I just can type it and it just goes and learn to play this game. We're not quite there, but this is a glimpse of maybe where we could go with this kind of technology.
You're right that it does really bring us back to that thing that you were doing so many years ago, which was something that could use a keyboard and a mouse, right? It's a really similar thing. Yeah,
even the actions are very similar, right? And understand the screen. And given what you ask, where would you click and so on? That's kind of the same sort of actions even that very general games would have to interact with. The difference is the goal there is narrow. It's just one game and the same kind of screens, whereas here is the whole web, which is pretty vast.
Well, okay, but then, so I'm sort of imagining what you could do now. Could it look in your calendar? Could you say, I want to go on holiday next year? And it could look in your calendar and work out when the best week was, know your budget, et cetera, et cetera, et cetera.
Yeah, so these models are not far from being able to automate this, right? So now it's a matter of making it better, right? Making it safe. There's a lot of steps. But if you just fast forward, anything a human can do on a browser, like these things can do in principle. And then if you make them really understand what you want and really good and through thinking and other techniques, they'll get better and better, and they'll be probably faster and maybe in some cases much better than you are doing those. So that's kind of the dream. And this is super early stages, but is also super exciting. And I think certainly next year, we're going to see a lot of experimentation around these idea of intersecting, language models agentically with, browser or computers more generally.
How about coding?
Yeah, coding is a great one as well. We are also releasing tools for software engineering, which, of course, they generally require not only, hey, here is a perfect description of a puzzle about coding, and please write me the code. And by the way, I know how to test it. It's more iterative, right? You have to write code, run the code, and so on and so forth. So we're putting that capability as well forward with, from an agentic point of view. We're also, games are very important. And of course, that was means to an end to develop powerful algorithms. But it's also very interesting to think about how these very powerful multimodal models start to understand games and can aid users to, entertain during like a game session, give them advice, or tell a joke about the game or whatnot, right? So we're also experimenting with this sort of game companion.
Okay, all of these things that you're talking about, this is sounding very close to intelligence that is quite general. Are we getting close to AGI?
Yeah, this is a good question. Look, I was thinking about this earlier this week. If 10 years ago, 5 years ago even, I would have been given the models today, right? And I would say, look, there's a secret lab. This is a model. Play with it and tell me if you think this is actually like close to a general intelligence. I would have claimed, oh yeah, that comes from a future where AGI is basically either has happened or I can see that this is very close to it, right? So the closer you are, the more you find, oh, but it hallucinates. Of course, that's very important, right? But I think just zooming out, it just feels like, okay, it's getting pretty close.
But then DeepMind's mission statement, solve intelligence, that sort of intelligence, like super intelligence, something that surpasses human intelligence. Do you think that scaling is enough to get us there? Or do you think that we need something else?
Yeah, Google DeepMind has this mission to obviously intersect intelligence with science to push the boundaries. And we've seen a good example very recently, of course, with AlphaFold. So in that sense, right, from a domain's perspective, we honestly have seen some examples already of narrow but super intelligent system. AlphaFold was only doing that. And I think probably that's the domains to think about where we're going to start seeing super intelligence, even from the general sort of capabilities these models have. You might need to do some specialization. And again, it might be worth it. Was it worth it to solve protein folding?
Of course.
Absolutely, right? But I think that's a good test to use, and we are very well positioned because we of course have like the whole of science team and so on working on very interesting problems. Now, if you take the language models and you start thinking about agents, putting them in environments that could be more about science, simulation, theorem provers, and so on, will something very discrete be needed to enable other breakthroughs? I would say probably not. Without another transformer-like breakthrough, perhaps, feels like we're going to start seeing more examples of, oh my God, like in math, now it just discovers new theorems that mathematicians find interesting. And it happened by just, of course, very good execution plus scaling up of some of the ideas and so on and so forth.
It is interesting, though, that the first dominoes to fall are the ones which have a ground truth, right?
Yeah.
Like science, as you described.
Yeah. Although, science, it depends which sciences might have ground truth, I suppose.
Protein folding definitely is.
Yeah, it's true. I'm hoping we also see some other ways to advance in a superhuman way. Like you could imagine having a brainstorming scientific advisor that is powered by one of these powerful models, and more than it discovers something or it proves something new, it just challenges your assumptions and it makes you think out of the box in a way that then my creativity sort of gets me to a place I couldn't have gone. Then you would call that superhuman in some ways as well, right? So I think those are definitely not out of scope and much harder to also, of course, think of how do you reward that behavior.
Absolutely fascinating. There was definitely a lot of drastic stuff in there.
Yeah, yes.
Thank you so much for joining me.
Yeah, likewise. Thanks. Pleasure. See you in 5 years.
I think there was this real theme that emerged from that conversation, at least for me anyway, which was this idea of generality. And if you think about it, there is this generality in the way that intelligence advances knowledge. Like those old astronomers like Copernicus, they were assessing lots of data from observing the sky and using that to extract a model of the solar system. But in the case of AlphaGo, it was observing games of Go to extract a model for the best possible way to play. And now, somewhere embedded in everything that has ever been created by humans is this model, this underlying truth of how we experience reality. And the model that we're looking for, of course, it's never going to be as neat as heliocentrism, but that model does seem to be in there, hidden among the frozen weights of Gemini. Now, if that's what we've done so far, the next phase is to try and use those general ideas to extract a model of human preferences too. And that is, of course, a lot harder. But if we succeed, it might just get us to a more general form of intelligence too, AGI. Now, if you found this conversation interesting, I think it's worth also checking out the episodes I did with Jeff Dean on, among other things, scaling, and Yason Gabriel on the ethics of AI agents. Or if you want to dig a bit deeper into the development of Gemini 2.0, then you can check out the latest episode of the new Google AI Release Notes podcast with host Logan Kilpatrick. This and other episodes can be found wherever you get your podcasts. Until next time.